Good day everyone. Now we'll try to explain. I'll try to explain regarding how to use the UART to control the speed of a DC motor. So basically I'll be using two microcontrollers, two LPC2148 microcontrollers. One will be transmitting the signal, and based on the signal the other microcontroller will be deciding the speed of the DC motor. So let me go to the program. So this is the program for transmitting. That is like what I have done is I have used one of the microcontrollers ADC to feed in the signal. So already I have made a video regarding ADC based DC motor speed control, wherein I have used that analog signal to control the speed of DC motor. The same concept is being used here. Only difference is I'll be using the UART to transmit whatever the analog signal which has been converted to DC in a single microcontroller to the other microcontroller. In the other microcontroller I'll be using a PWM of that microcontroller to change the duty ratio, so you will get a variation in the speed. So in case if you want to know about how to use that ADC to have the speed control, you can watch that video first and then come to this video. I mean, it's not mandatory that you have to watch that one, but you'll get an idea in case if you do watch that video. So here as in my previous videos, this part is concerned with initializing the registers memory address with the labels. So we'll use it inside the code. So now first I'm initializing this pin cell 0. So pin cell 0, I'm using it for initializing UART pins. So so here you can see that I have put a value 050000 into R1, and R0 is having the pin cell 0 registers memory address. So you all know if I'm writing LDR R0 comma equal to pin cell 0, this memory address E002C000 is copied into R0, which means that R0 will be having this address of pin cell 0, and I'm moving 50000 into R1. So the R1 content, that is 50000, is moved into the pin cell 0 register. So let us see what does this 50000 means. So if you see it in binary, you can see that this 18th and 16th bit is active in the pin cell 0 register. Let us see what is the significance of this 18th and 16th bit in pin cell 0 register. So you can see 18th bit I am making it as high, and 16th bit I am making it as high, right? So 16th bit mean 17 and 16, if I am giving 0 1, that is activating the transmit pin, and 19th and 18th pin I am making it as a 0 1 to give that receive pin. So as far as this program is concerned, I will not be receiving anything, but for future expansion I'm activating both the pins, transmit and receive. But as far as this program is concerned, if you do only this transmitting activation, that will be sufficient. So let me go to the code again. So pin cell 0, first I am initializing the TXD and RXD pins. Then pin cell 1 register, I am activating this AD0.3. Why I am doing AD0.3 is I am using the pin I mean, I'm using the potentiometer that is available in the board itself, that is NGX blue board itself, to be connected towards the ADC, so that would be easy for me to make any changes, or when I need it, I'll try to rotate the potentiometer to get a different analog voltages. So otherwise, in case if I am using other channels, AD 0.3 means AD analog to digital converter 0 and channel 3. If I am using other channels, I need to have a hardware circuit which should be connected to the concerned pin. So let me check the pin cell 1, right? So in pin cell 1, this 1 represents this 28 bit is high, right? So this 28 bit is associated with the AD 0.3. So let us check that once. Pin cell 1, 28 bit. So you can see 28th bit I am making it as high. So 29th is 0 and 28th is 1. So 0 1, if you give, AD 0.3 is associated with pin P0.30. P0.30 is the analog input pin that I am going to connect with the potentiometer. The potentiometer available in the board itself. So this is for AD 0.3 and this is for transmit. Then I'll be using ADC interrupt. So because I want the conversion to happen continuously, and at the same time the conversion, whatever it is happening, should be taken care by the interrupt to transmit it. So the transmit program, I'll be writing it in the interrupt service routine, right? If you could see, the initialization of the UART is done in the main routine, while the transmitting I'll be doing it in the interrupt service routine. I'll explain that in detail later. So let us go in the sequence that is available. So now I'm coming to this VIC interrupt enable. So let us check what is the value 40000 is indicating. So VIC interrupt enable, this 40000 is indicating that 18th bit is high in the VIC interrupt enabled register. So let us go to the VIC interrupt enabled register. So this is VIC interrupt enabled register, wherein you can see the 18th bit is active. So if you activate this 18th bit, your analog to digital converter 0 gets active. Okay, so analog to digital converter 0, I am activating that particular bit, so that when conversion happens, interrupt will happen. So if I make this bit high, analog to digital converter 0 is connected to the interrupt activation I am doing using this VIC interrupt enable register. Coming back to the code, then VIC interrupt select, I am going to use it in IRQ mode, so I am placing 0 into it. Then VIC vector control 0, I am activating, I'm placing 32. So vector control 32 in the sense here you can see that 5th bit you should be activating it for slot enable, and the bits from 0th to 4th bit you will be allotting it for the slot number, right? So let us see the VIC vector control register. Yeah, this is your vector control register. As already I have told you, 0th to 4th bit is associated for the slot number, and 5th is your slot enable. So 5th bit I am activating, that is the slot enable, while 0th to 4th bit, the slot number I'll have to put it over there. So here you can see, if you take the slot number, you will get it like 12. right? So leave this one, you will get it like 12. Since this slot enable is coming, then it is becoming 3. So if you are not having this slot enable bit, so the rest of the bit you will make it as like 1 2, right? So how we are arriving at this 1 2, right? So you can check it with the any of the interrupt registers. Possibly we'll go to that interrupt enable register itself. So here it's given 18. So 18 is in decimal. If you convert 18 decimal into hexadecimal, you will get it as 12. Let us check that one. 18, so convert it into hexadecimal, you are getting 12. So that is the reason you are mentioning 12 over here in the VIC vector control. This one is slot enable, so this is the 12 is the slot number. So slot number you can obtain it from any of the registers. So I am activating the ADC 0 using this VIC vector control register. Then coming back to the code again, then VIC vector address 0, I am making it like IRQ handler. So as I have done in any other interrupt program previously, I will be commenting over here IRQ handler be IRQ handler, and I can use this same label. So that I have done over here. Then AD0 interrupt enable register, so I am making 08. So AD0 interrupt enable register, I am activating this 8th bit. You can see 0th, 1st, 2nd and 3rd. So it follows this 8421 pattern. I think you can understand this. So this is like a conversion of the hexadecimal into binary, right? So here you will see the hexadecimal, and here the binary value is placed, and this is the bit number. So this will, I mean, this particular structure will help us to understand which bit is active. So I have made this one. So let us see what is this what is the significance of this particular 8th bit in AD0 interrupt enable register. Yeah, AD0 interrupt enable register. So I am activating this 3rd bit, right? So here 3rd bit. So this 8 is concerned with its weightage 8421. 3rd bit I have made active, right? 3rd bit I have made active. So that 3rd bit signifies I am activating AD interrupt channel 3. I mean, AD interrupt should be generated when channel 3 is converting an analog to digital conversion. When that conversion is happening, this will create an interrupt. So in the interrupt service routine, I will be fetching the value from the concerned data register and pushing it into the transmit buffer. So that is concerned with your AD0 interrupt enable register. Coming to this AD0 control register. So AD0 control register, I think we have discussed in analog to digital converter video, and possibly in the ADC based speed control of DC motor also. So I am again discussing that in detail, so that it won't be required for you to go and visit that video again. So this is your AD0 CR format. You can see that here, starting from your first bit, these are all like concerned with your channel select. So individual bits are connected with individual channels, right? So if I'm putting 1 over here, it activates the 0th channel, which means AD 0.0 will get activated, or 1.0 if I am using analog to digital converter 1, and 1.1, 1.2. So corresponding bit is connected with the corresponding channel, and this bit is concerned with the clock division. So this decides on two things, that is your how much clock will be spent for conversion, and possibly the number of bits that you want to generate. So let us once look into the analog to digital converter control register again. Yeah. So here you can see clock division is for the VPP clock only, right? So it's not for deciding on the number of bits. It specifies the amount of clock that might be, that has to be sent towards your analog to digital converter. So that you'll be, the number whatever you want, whatever the slashing factor that you want, you will be specifying between 8th and 15th bit, while 16th bit is for selecting between bust mode or software control mode. So in this program I will be using this bust mode, while this 17th to 19th pin, right, 17th to 19th pin will be used for clocks and number of bits. So initially I said regarding this is only for clock division. This 17th to 19th bit only will be used for specifying the number of clocks that has to be spent for conversion. At the same time, what is the number of bits that you want to specify. So as in this program, I'll be doing it with 10, not with 10 bits. So 10 bits is the maximum bit that I can choose for, but since the UART transmission can happen at the maximum with 8 bit only, so I'll choose the number of bit as in this case also with 8 bits rather than 10 bit. In the previous ADC based speed control of DC motor, I would have used 10 bit ADC. So here I'll be choosing 8 bit ADC. So let us check this one again. So I'll be choosing this 8 bit ADC, right? So 9 clocks will be used for conversion. So then the 21st bit is for bringing your ADC from power down mode to operational mode, and 26 to 24 specifies the start. So this becomes meaningful only when you have this software control mode. If it is bust mode, then this doesn't have any control, and once this is available, then only this edge will have significance. Which edge should start the analog to digital conversion is decided by this 1 and 0. So again, this becomes meaningful only when you have the software control mode. So as in this case we are not using software control mode, so either this 27th bit or 24th to 26th bit is like not having any significance at all, right? So in clocks we have specified this 5, which is 18th and 5 in the sense like I'm making it as 0 1 0. So this is 0 1 0, as I've already shown you, makes your ADC converter to work with 9 clocks and create a 8 bits. The conversion will happen with 8 bits. So this one I am selecting over here. So that I have made here, and that is like 0 1 0, and this 16th bit is like I am using this bust mode, right? So then with the case of this clock division, I am keeping it F, so that my conversion will have a bit slower type of conversion. So if you are trying to keep a minimum value, it might go faster, sometimes it may not work. So I have used the same f in the previous case also, previous ADC based speed control also. I am using the same value over here, and this 8 signifies that I am activating this third channel, 0th, 1st, 2nd, 3rd, AD 0.3 I am activating, so that I am specifying using this 8, and this 1 is, this 2 is making your ADC to go to power up mode, right? So this is the explanation for your AD0 control register. So coming back to the program again, so that is the reason we have, whatever we have analyzed and placed over here, I have added inside my program. So this is concerned with your AD0 control register. Then coming to the U1 LCR, right? So U1 LCR I am making it as 80, right? 80 signifies the 8th bit is high and the remaining all the bits are 0. So U1 LCR format has been represented here. Your 8 bit is connected with the DLAP, while the remaining bits is like your sorry, it's a 7th bit. 7th bit is like DLAP, and 6th bit is like brake control, and 5th and 4th is parity select, and 3rd is parity enable, and 2 is stop bit select, and 1 and 0 is word length select. So what is the word length? We'll be providing 8-bit word length, so that will initialize it later. So here first initialization what I'm doing is DLAB, I'm making it high. So for activating or using any of your UART register, you need to activate this DLAB first. So let us see the DLAB, U1 LCR line control register first. Yeah, this is your line control register. So here probably the word length, 8-bit character length, I'll be giving it later. So I'll have to give 1 1, which means that I'll have to provide 3 into the U0 LCR register. That maybe I'll do it later. And here you can see the second bit is like stop bit select. So 1 stop bit or 2 stop bit. So since I'm giving 0, it will be 1 stop bit. And third is parity enable. If you're 0, there is no parity generation, so I haven't selected parity. In case if you are making it 1, then you can have the selection between odd parity, even parity, and with a sticky parity. Those things you can go for selecting it, and you can activate with brake control also. So if there is like if you want any brake transmission, that brake control you can have. So as in this program I haven't used the brake control, and this is your divisor latch access bit. So you need to make this access bit high to make any if you want to make any changes to the UART concerned register, this one has to be made high, right? Going back to the code again, then I'm using this U1 DLM and U1 DLL. So these two registers will be used for fixing the baud rate. So let us see the baud rate calculation. So U1 LCR I have given 80, and possibly at the last I'll be making it 03 to make the character length, right, 8-bit character length. So to decide on what should be the U0 DLM and DLL, you have this formula. This is the formula, right? So let us see once the structure of U0 DLM and DLL again. Yeah, this is your DLM and DLL register, which is you can see 8-bit registers, right? So these two registers will be used like part of the divisors, right, that you are going to use it for generating the baud rate. So in addition to this DLL and DLM, you will be using this fractional divisor register also. So as in this code I haven't used this fractional divisor register. So for a baud rate to be generated, so you can use a calculation to find out what is the nearest value of the baud rate that you require, and possibly you can use this fractional divider register to navigate between or to make a precise value of the baud rate. So as in this program I haven't used this fractional divider, but you can always use this to make a precise value of baud rate. But whatever the baud rate that you have kept for the transmitting microcontroller, the same should be kept for the receiving microcontroller also, right? Going back to the calculation over here, you can see this is the formula. So P clock, that is the peripheral clock, divided by 16 into U0 DLM plus U0 DLL into 1 plus divide div add value divided by mul value. So div add value can be 0 or any value, and but mul value should be always 1. If you are placing any other value also, it will be taken as like 1, right? So as I've already told you, I'll not be using this part, so which means that your divide add value will be automatically 0 and the mul value will be automatically 1, right? So the maximum value that you can feed in these two is like 0 to 15. Okay, so in this program I have made the baud rate for 1932. So to get this 1932, I have made the DLM as 0, div add value 0, and mul value as 1. So I haven't initialized any fractional divisor register, so automatically my div add value will be 0 and mul value will be 1. So peripheral clock is 3 megahertz, so that is like 3000000 hertz, right? Having obtained this peripheral clock, I'll use the formula that has been given over here for calculating the value of U0 DLL, right? So 1932 is the baud rate that we require, that is equivalent to 3000000 divided by 16 into U0 DLL, because I have made U0 DLM as 0. So if your U0 DLM is 0, 0 into 16 becomes like 0, and the value U0 DLL only will be multiplied by this 16, and this value is like multiplied by 1 it will become, because divide add value is 0 and divided by 1. So 0 by 1 is obviously 0. So 1 plus 0 will become 1. So having obtained that calculation, so I am putting the value 1932 equals 3000000 divided by 16 into U0 DLL. So U0 DLL becomes equivalent to 3000000 divided by 16 into 1932. So that happens to give me a value of 97 in decimal, but I need to use it in hexadecimal inside the code. So when you do the conversion, it becomes 61 hexadecimal. So you can see I have used the value 61 in U0 DLL. So U0 DLM is 00, U1 DLM is 00, U1 DLL is 61. So this also should be U1. So it's a typo error, because like I'm using UART 1, so everything should be represented with U1. Okay, fine. Okay, now I have made the DLM and DLL for the baud rate 1932. Then U1 LCR I am giving 3, so that I'll have a character length of 8 bit, so that we have already seen. As previously said, I am making this word length bit 0 and 1 as like 1 1 to have 8 bit character length, so that I am initializing over here, right. Then coming to this IRQ handler, so whenever the conversion, analog to digital conversion, is happening, it comes to this IRQ handler. Right, in the IRQ handler I am using this SUB LR LR #4, which means that that is the fixed value of offset, which you will have to subtract in the link register for proper operation of your interrupt service routine. I am storing the LR into R6 so that to save the content in case if LR is being used for other purpose. As in this program, this is, if you are not doing this also, the functioning will be good, because this becomes meaningful only when you have interrupt service routine and a subroutine, right. If you are not having any other subroutines, as in this program I don't have any subroutines, so if you are not writing this also, it is fine, but it is a best practice to have this to avoid any confusion. So here what I am doing is I am reading the content of AD0 DR3 by putting the address of AD0 DR3 in R3 and reading the value of AD0 DR3. AD0 DR3 is the data register, analog to digital converter data register of channel 3, right. So I am whatever the value that I have read, what I am doing is I am ANDing it with FF00. Since this is like 8-bit ADC converter, the value will be available only in these bits, right. So the starting from you can assume that this is like starts from 0 to 7th bit, so this is like 8th to 16th bit, sorry 15th bit. So 8th to 15th bit will be the part where you will have the data. Let us check once this AD0 DR3. AD0 DR, it can be channel 1, 2 or 3. It will have this format. You can see that you have this 31st bit for done bit and 30th bit for overrun bit, and 29th to 16th bit is reserved, and 15th to 6th bit is the result that will be available if your ADC is of 10-bit version. So we have selected 8-bit version, so your 8-bit will be selected from starting from here 15, 14 and 13, 12, 10, 9, 8. So up to this only you will have the value. So this will be counting to F, and this will be counting to another F. So FF. So this will be discarded because our ADC is of 8-bit version. Then so I am ANDing it so that I'll be extracting only the data that has got converted from analog to digital, and I am placing it in the R7 register. Then I am doing this logical shift right. So why I am doing 8 times is like in the previous version of the program I would have done 6 times, but here since the value you can see that is like 2 bits beyond this point has gone towards here, so it should come like 8 bits towards the right side. So in the previous case it was like almost 6 bits you need to go on the right side. In the ADC controlled, ADC based speed control of DC motor, I would have done LSR with 6 times. So in this case I need to do 8 times, because of the reason that my data is available from 15th to 8th bit. So 8 times it has to go towards right, so that your data becomes meaningful. Otherwise your data will not be meaningful. So that I am doing here. So for checking it, I am putting the value whatever I have rotated into a memory address. So this you can skip also, right? To check whether analog digital converter is working properly, I have done this one. So for real-time application this may not be necessary also. Then what I am doing is like I am using this transmit hold register, right? So what is the function of transmit hold register? The content that I have obtained from here should be placed in the transmit hold register, and it has to be sent transmitted to the other microcontroller, right? So let us see the transmit hold register once. Yeah, this is your transmit hold register. You can see that is a 8-bit register. So towards this 8-bit register I am moving the content whatever I have extracted from the data register. Then once I have done that, I am activating the transmit enable register. So let us check the transmit enable register. Yeah, this is your transmit enable register. I am activating this 7th bit, right, 0th to 7th bit. So I need to activate this to make the transmit happen. So once this is done, your value whatever that has got converted from analog to digital is transmitted through the UART, right? So then I am flushing off the VIC vector address, and then I am returning back to the main routine. So main routine, it will stay over here, while the ADC will be taking care of converting the value and sending it to the remote microcontroller. So this is the transmit part. So in case if you want to check, we'll check it by simulating it. I have made the hardware for this particular code, both the transmit and receive. It becomes meaningful when you work with the real hardware rather than simulating it, because in this simulation we can just check whether data is getting transmitted. Whichever the analog to digital conversion that is happening is getting transmitted or not. So let us use this AD converter 0.3 I have used, and possibly so in AD channel 3, let me keep a value 1 over here. So it is sending a character over here. So UART window, the serial window always gives you the value in terms of ASCII. So it takes in ASCII and displays it as a character, as a some character. So whatever the changes that you do will get transformed into some kind of a alphabet. So that alphabetical character change is happening, you can see. So once when you can see from here, the from m, the it is changed to some greater than symbol, right? So each value will have its own significance. Let me change it to possibly 3. So it is showing some special character. Anyway, so this is like to show you that whatever the change that I do with the analog to digital converter channel 3, it is getting transmitted over here, right? So this is to check whether our code is working. Yeah, this transmit code is working. Okay, now we'll discuss about the receiving end microcontrollers program. So in the transmitting microcontroller, we'll be using ADC, and the ADC value whichever that has got converted to digital, we are transmitting it to the other microcontroller. In the other microcontroller, that is remote microcontroller, we'll be receiving the digital value, and after it has got received, we'll put the value into the PWM. So the PWM's duty ratio will be decided by the digital value that is obtained from the sending end microcontroller. So in turn, that is dependent on the analog value which we are feeding into the analog to digital converter, right? So coming to this receiving end program, so first I am initializing pinzel 0 with 50002. So what is this 50002? Let us see over here. So we are activating this 18th bit and 16th bit and this first bit, right? So we have done this same 50000 in the previous program for transmit. That is like making your UART1 transmit and receive, and this 10 is used for activating your PWM1, that single edged PWM1 activating in P0.0. So let us check that once. The pinzel register, pinzel 0, right? So here in pinzel 0 register, we have already checked that 19th and 18th bit 01 I am making it receive, and in P0.9 I am making the receive pin, while P0.8 I am activating this transmit pin, right? So here in this program, in this receive program, if I activate only this P0.9 with RxD, that is sufficient because I am not going to transmit anything. So this is like for future expansion, I have made both transmit and receive active. Okay, now coming back to the code, U1 LCR. So U1 LCR we have discussed in the previous code. The same thing I am repeating again. That line control register. So I am making the line control register that D access divisor latch access bit as active high. Enable access to divisor latches. This is your line control register that I am making it active in the beginning, and then U1 DLM 00 and U1 DLL 61. So we have seen the calculation in the previous program. The same value you need to put in the receiving end microcontroller also. I am making the baud rate as 1932. To do that, I am putting the value U1 DLM as 00, U1 DLL as 61. Then U1 LCR I am making it as 3 so to specify the character length as like 8 bit. So zeroth and first bit, the character length, I am making it as 8 bit U1 LCR. U1 LCR. I'm showing the PPT with U0, but it doesn't matter U1 or U0. The pattern, the format of the concerned registers are the same. Only the memory address of the concerned register will be different. So then I am activating UART interrupt in VIC interrupt enable register. So 80 signifies in VIC interrupt enable register. Yeah, 80 signifies that I am activating the 7th bit, right? So what does that 7th bit signify? Let us check in the interrupt register. Interrupt enable register, 7th bit UART 1. So I am activating the UART interrupt. So whenever data is received, interrupt will be generated, and in the interrupt service routine I will be changing the PWM, right? PWM duty ratio. So to do that, I am enabling this VAC interrupt enable. VAC interrupt select, I am making it as 0x0 to have this IRQ handler, and VAC vector control 0, I am putting 27. So 7 is the slot number, right? So to see the slot number again, you can check any of the interrupt registers. So this is your slot number. In the previous case, if you could remember, we have used this 18, that is analog to digital interrupt. So in the transmit program I have used ADC interrupt, and in the receive program I have used the UART interrupt. So this is the 7 is the slot number. So your VAC vector control register, I am making it as 27, right? So 2 is the slot enable, while 7 is the number, right? VAC vector control 0. Then U1 IER interrupt enable register, I am making it as 01. So U1 IER, if I am making 01, I am activating this RBR interrupt enable. So your UART interrupt has multiple interrupt options. You can raise the interrupt when you want to, when your transmit buffer is ready. So that we have not done. As in this program, our concern is like when data is received, you need to generate an interrupt. So that activation is done in this 0th bit, that is RBR interrupt enable. So the rest of the things we are not using. So as in this program, so I am activating this U1 IER with 1 to activate the interrupt when receive buffer has the value. Then VAC vector address 0, I am making it as IRQ handler. So you can use the same label, because this is going to be dumped in a different microcontroller. This one in a different microcontroller, and this one in a different microcontroller. You don't have to worry about labels getting repeated with the transmit and receive code. Now from here I am getting into the PWM code. I have made videos for PWM programming also. So the same is repeated again. So here PWM PR is the prescaler register. PWM prescaler register, I am putting a value 2 into it, so that your prescaler is designed for 1 microsecond, right? And PWM MR0, I am making it 100 hexadecimal, right? Why I have given 100 is since the data that is received from your remote microcontroller, maximum will be FF. If 8-bit is the character length, obviously FF is the maximum value that it can have. What is the value if you add 1 towards FF? Then it becomes like 100. FF plus 1 is like 100. So 100 should be the PWM MR0, so that that is the your cycle, right? So it's like 100 hexadecimal microsecond. It's not 100 microsecond, it is 100 in hexadecimal, right? So if you want to calculate it, you can use the calculator and check. In hexadecimal I am giving 100. So 256 microseconds. 256 microseconds is the cycle. Then PWM-MR1 I am keeping 1 microsecond by default. So obviously when your microcontroller becomes alive, and when both the microcontrollers are communicating, this PWM-MR1 value will change. So PWM match control register, so I am making it as 2. So match control register, if I am making it as 2, I am activating the first bit, 0th bit, first bit high. So we have already seen that. Anyway, let us see that again also. That is regarding your PWM register. So let me open the PWM register. Yeah, this is the PWM match control register. So in the match control register, if I'm making this as 1, so interrupt will be generated when match register 0 content matches with your TC, PWM TC. So but we are not activating this 0th bit, we are activating this 1 bit. So PWM match register 0, when it PWM match register 0, when it matches with the PWM TC, reset should happen. So we haven't activated the 0th bit, we are activating this first bit. So that is the content. So reset should happen when PWM MR0 matches with PWM TC. Then PWM LER, latch enabled register. So if I'm making 3, it means that I am activating your 0th bit and first bit, right? So latch enabled register, both the PWM MR0 and MR1 has to be activated. That I am doing it with that latch enable register. So let me show you the latch enable register. Enable PWM match 0 latch, enable PWM match 1 latch, I am latching it. Then PWM PCR 200. So what does this 200 signify? It's like your 9th bit is high, right? So this is for enabling your PWM in single edged mode. Let me show you the PWM PCR register. Yeah, this is your PWM PCR register. So since I am not using the double edged mode, these bits will not have any significance. So this one I'll be activating. PWM1 output I am enabling using this PWM PCR register. Then PWM TCR2 and PWM TCR9. This is to reset the PWM timer counter. This is to start your PWM timer counter. Reset and start. So PWM TCR2 and PWM TCR9. Let us check again in the register, PWM registers. PWM, yeah, TCR. You can see if making this 2, it will reset the counter, right? You'll have to put 0th bit as 1 and 3rd bit as 1 to make the PWM and enable and counter enable. So 9 I am putting inside PWM TCR. So this is started. So in the interrupt service routine, what we should do is we should receive the content that has been obtained from the RBR, U1 RBR. So because like interrupt, I mean again in this case the program comes and stays over here, and the interrupt will take care of receiving the content and changing the content inside your PWM MR1. MR1 takes care of your value match, that is your duty ratio, because MR0 is for the cycle while MR1 is for your specifying the on time, since this is like single edged mode. So what I'm doing in the interrupt service routine is like first sub lr comma lr comma hash 4 as we have done in the previous code. It's the default offset that you'll have to subtract. Then I'm storing the LR into R6. Then I'm reading the content from, I mean, this is like address I'm putting in the R0 and I'm reading it into R3. R3 will have the value that has been obtained from the remote microcontroller. Then I am initializing PWM MR1 into R0, and whatever value that I have read into R3 I am putting inside the PWM MR1, so that once the content is placed inside the PWM MR1, and when you do this latch, your PWM changes will happen. And this is like to flush off the BIC vector address. And once I have changed the value inside the PWM LR, I am returning back to the main routine. Main routine again, it will stay over here, right? So again in this case also we can check the working of the microcontroller, but the complete working becomes meaningful only when you dump it in the hardware, which comes next. Here just I'll show you whether this code is working or not. So this is not required, so I'll use this logic analyzer. Port 0.0, and now you can see the value is getting obtained. That is like 1 microsecond is the time delay. Let me have some other value. So I am putting 2, 3, then 4. Different values I have tried. So whenever I am changing value, you can see that your time delay is varying. Once I reset again, it goes like this. When I press 0, I mean here what happens is like here in this window will transmit the content in terms of ASCII, whatever that content that I'm typing. If I'm pressing 0, 0 will be converted to ASCII value. So that ASCII value is getting placed in the PWM MR1, right? So 0, 1, 2, 3. So you can see that the change increment in the time delay is like very meager, because 0 is like almost equivalent to 30, I guess, for ASCII. Then 31, 32, 33, it goes on like that. So your waveform also will happen in that sense. Your on time also will happen in that sense. So it goes on like this. Okay, regarding the hardware, we need to look into from which pin we have to obtain the pulses, and from which pin to which pin has to be connected for making the communication, right? So we have used the UART 1 with transmit and receive, possibly from P 0.8 and 0.9, right? P 0.8 is like transmit and 0.9 is for receive. So as I've already told you, in this particular experimentation, for one microcontroller I'll be using the transmit, and the other microcontroller I'll be using the receive. So I need to check in which of this J connection this is connected, J1, J2 and J3. So if you see in J3, first and second pin or the pins that is concerned with your UART. So P0.8 is transmit. So from the first microcontroller in J3 first pin, I'll be connecting it to the second pin of the second microcontroller, that is receive. So transmit has to be connected to the receive, and possibly the 10th pin I'll be connecting it common ground between these two microcontrollers. Right. So to obtain your PWM 1, right, P0 underscore A0, I will be using this third pin of J2, third pin and second pin. Third pin is PWM and second pin ground, right. So this I'll use it in the hardware. This is the program for the transmit microcontroller, wherein ADC interrupt I have used. ADC interrupt is used, wherein ADC, whatever the analog value that we are feeding through this potentiometer is getting converted to analog, and that is being transmitted to the other microcontroller. So now I'm translating, building and rebuilding, and I'll check the where the hex file is created. So it is in this objects folder. So let me dump that code. So whose so this is the file, hex file that we are supposed to dump in the microcontroller. Now I am dumping the same. So now transmit microcontroller's program is dumped. Next is receiver microcontroller's program. So I'll delete this and I'll remove this. I'll add the receive microcontroller's program. So I have added this. Now I am doing translate, build and rebuild. So I am not changing anything over here. So I will dump the same arm.x using the flash magic in the second microcontroller. So now I am dumping this. Code. So both the programs has been dumped. So now pass. Now start. So this is your transmit microcontroller and this is your receive microcontroller. In transmit microcontroller, in J3, first pin will be used for TXT and second pin will be used for RXT. First pin of J3 is connected to the second pin of J3 in the receive microcontroller, while 10 is the ground pin for both the cases. Then in J2, third pin is the positive of PWM and second pin is the negative. So this third and second pin in J2, I am connecting it to the optocoupler TLP350 in second and third pin. Then between 8th and 5th pin I need to provide a voltage of around 13 volt, and 6th pin I am giving it to the gate of the IGBT, and towards the collector I will be giving the V in. So whatever the voltage that we have to feed into the DC motor, that I am supplying it to the collector, and from emitter I am connecting this DC motor, and on the other side it is connected to the negative pass. Okay. Now over here, this is the J3. In J3, as I've already told you, the number 1 pin, I am connecting it to the J3 number 2 pin. This transmit is connected to the receive, and this is the ground pin. 10th pin to 10th pin, I have connected the ground pin, and from the J2 connection, I am having this second and third pin. Third pin should be connected to the positive of the probe, and second pin to the negative of the probe. Right. So now the connection for checking whether the transmitting is happening is being done. Now I'll change this potentiometer. You can see over here normally some duty ratio it is appearing. You can see now I am varying this potentiometer. So you can see the duty ratio is getting varied. So communication is happening between this microcontroller, this one and this one. So this one is telling what should be the duty ratio, and this one is deciding on depending on whatever it has got transmitted. So this is the way in which it is communicating. I am using 2 wires for communicating. Pass. Now we have connected this optocoupler. You can see from third pin I have connected to the third pin from J2 of the receiver microcontroller. I have connected to the second pin of the optocoupler TLP350, and second pin I have connected to the third pin. Second pin of J2, that is ground, I am connecting it to the third pin of the optocoupler, and the optocoupler 8th pin I have connected to 12 volt. I mean 12.7 or 13, we can give it 13 volt, and negative I have connected to the 5th pin of TLP350. Right. So now for checking the optocoupler's operation, I have connected the probe between 5th and 6th pin. So 6th pin will be positive on the yellow wire, that is 6th pin, and this is 5th pin, that is negative. You can see that optocoupler, your voltage has got increased. If you want, you can raise the voltage also by varying this one, but minimum voltage is sufficient, so we can keep it like 13 volt. And now I will show you the variation with the potentiometer again. So you can see now I am varying in the optocoupler's output also. Your pulse width is varying. Pass. Okay. Now we have made the chopper connection, and across the load we have connected the DC motor. You can see that already it is rotating with a minimum speed, and further when I decrease the PWM, you can see that it is rotating with minimum speed, and when I increase the pulse width using this ADC, you could see that the speed of the motor is like running faster. You can see the PWM maximum over here, so I will make it maximum. So now it will be rotating with the maximum speed. Again I am reducing the speed. So it is rotating with a very minimum speed over here. Thank you.